Welcome to lecture 42, which is on geometric corrections applied to the satellite image. In this lecture, you will learn what are these geometric corrections and why the geometric correction is to be applied to satellite images before classification. So, let us start the lecture. There are geometric distortions which are present in the satellite image, or as a matter of fact aerial photographs also, and they are caused by the position, the size, orientation of the pixel, which are altered while this data is acquired, because we are acquiring the data of a three-dimensional Earth surface and then projected on a two-dimensional surface. So these raw images, when you look at those images, they will have some geometric errors, and the reasons for this geometric error could be many as listed over here. It could be variation in the altitude, attitude and the velocity of the sensor platform. So raw pitch and yaw of the sensor platform who is taking these images, it is, if there is a variation in that, it is panoramic distortion. So when you are taking a panoramic view of a large view of the area, there are distortions taking place due to the curvature of the earth. As we told you that this earth is a three-dimensional surface and there are curvature on the earth, ups and downs. So due to the curvature, if the area covered is large, then also we have atmospheric refraction. We have studied the effect of the atmosphere on satellite images. Refraction is one phenomena due to which we have some geometric distortion present. Relief displacement, we know from our background knowledge of photogrammetry that different objects with different heights will cause the relief displacement in the image. Then if there are known linearities in the sensor system which has been used for taking those images. So all together, combined effect, we get the geometric distortion. We may not know exactly for what reason, exactly what is the parameter for which that geometric distortion is present, but it is the combined effect of all these parameters. So what they are actually, what this error is doing, this error actually is changing the spatial characteristics of the picture. So the location of the pixel with respect to its true position, when we define the pixel coordinates like x and y coordinates or latitude and longitude coordinates, so it is displaced, then one pixel relationship with the other pixel because of the distortion. So actual measurement on the ground and the measurement on the photograph or the images should come out to be the same, but they are not same because of the distortions which are present and pixel size. So these are all the processes which are changing the spatial geometry of the images, and a process called resampling. In fact, the geometric corrections, georeferencing and resampling, they are done together. So in the resampling also the radiometry of the pixel is changed. So these corrections are necessary to apply because we want to eliminate the distortion which are present due to the characteristics of the sensor. So different sensors which have been employed to take the images and the characteristics of the terrain, curvature of the earth, viewing angle. So all these parameters will cause the distortion and we have to eliminate the distortion. Then there could be distortion present because of the projection system. We are projecting three-dimensional earth on a two-dimensional image. So we have to select a projection system, projection system, so that we can maintain either the distance, we can maintain either the area, maintain either the shape of the different objects. Change the pixel size. So this is important. When we are changing the pixel size, the correction has to be applied from one pixel size to another pixel size, as we are doing in the resampling process. Now, if we have to carry out accurate measurements from the images, then it is very important measurement regarding the distance between the 2 point length, area measurements. So, if we carry out all these measurements from the photographs or the images, it is very important that we apply the geometric corrections to that. If we want to compare the analysis which has been carried out from these images with the actual ground, and it is very important because when we are analyzing the satellite image or any digital image, we are applying these results to the earth surface. So, you cannot match the result together, you cannot transfer your details together, you cannot compare them together if the geometry of the image and geometry of the earth, they are not same. So, it is important for that purpose also. Now, many times when we are doing change analysis and we want to see the pattern and we want to predict something on the basis of the previous pattern, we want to see the historical developments in the area, what has happened in the past. So, we need several images which are to be analyzed together, compared together. Sometimes a quantitative analysis has to be done with those images. So, when we are doing that, they have to be geometrically corrected. If they are not geometrically corrected, then we cannot compare them together, we cannot derive the results. One image will not overlay over the other image because of these problems. And those who are using GIS, they must have faced also that if they have a map like a revenue map and try to superimpose onto the satellite image, it will not match because of the georeferencing. Georeferencing is not there and there are errors which are present, and that is why this is happening. Now, we have to use many times the results of our digital image analysis along with the other data in GIS, Geographical Information System. So, you can use them together when there is a common scale, there is a common reference system, there is a common datum. So, this is very important aspect. You cannot actually use the data in isolation along with the other if the geometry is different, if the coordinate system is different, if the datum is different. Many times you are creating the mosaic also for a large area. Your area may not be covered in one single scene, so you are joining them together. If you join them together and they are not geometrically corrected, they are at a different orientations, then again there will be a difficulty to create a mosaic. So, these are some of the uh, points, some of the parameters which are necessary. Actually, geometric correction is necessary to apply in order to take care of these things. Now, there are two things here. One is the image coordinates. When the different platforms are taking the images, so they are taking the images and these image coordinates are in terms of the line and pixel number. So, normally line and pixel number is denoting the coordinates of those pixels. But we have altogether a different system which we call the real world coordinate system when we are talking of latitude and the longitude. So, those real world coordinate systems we are talking in terms of the latitude and longitude, and this is shown diagrammatically here. So, this is the object coordinate frame which is shown. There is an object on the ground and there is an object coordination frame on which x, y and z are marked. So, any point on the globe on the earth surface can be represented in terms of the real world coordinates, latitude, longitude and the height of that point. But there are different platforms, like you can see here, there is a camera, maybe in the aircraft, maybe in the UAV system, there is a laser device, then there is a GPS and IMU also, which is trying to actually coordinate, trying to establish a relationship. But if we are using a camera system or a laser device or a sensor system, we are getting the images in altogether different coordinate system. So, our job is that the image coordinate system should match with the ground coordinate system, so that we can georeference the two together and use them together, compare them together. So, in order to do that, this slide shows that the top one is the image and there are certain points on the ground. So, this is one point, the second point and a third point, which is lying at a different terrain height. So, this is the terrain which shows that different points are lying there. Now, the geometry of the image which has been taken by a remote sensing platform may not be exactly same as the geometry of the earth, because when we are talking of the earth and when we are preparing the maps of the earth surface, we are orienting them with respect to north. So, our engineering maps are normally oriented with respect to magnetic north, but the army and defense people prepare map with respect to true north direction. So, for us those latitude and longitude lines are very important, north direction is important, because we have to orient the map in that direction, and so that we can compare, we can match the detail. So, down below figure is the oriented figure with respect to earth, and now there is one-to-one match, as far as the details are concerned on the ground as well as on the satellite image. So, earlier one was slightly rotated, and now this another one image is now rotated in a different directions. Anti-clockwise if you rotate it and carry out some kind of a scaling and some kind of a transformations, then you can get the image, corrected image, whose geometry is same as the geometry of the ground. So, this is what exactly we are doing. Now, this diagram shows that if we are using more than one image, we are using two images. Suppose we want to see the stereo model, so their orientation also should be same, geometry should be same. So, here there are certain points which are on the ground here, and in the photograph those points are appearing. Same points on the ground and they are appearing in the two successive images. So, we can find out the coordinates of these points. On one image, we can find out the coordinates on the another image, and if we use some kind of a transformation, so that these two coordinate systems, because they are the common points, overlap with each other, merge with each other, then we can create a 3D model. And this is what we are doing actually in creating the digital elevation model from digital images, digital photographs. So, here also we are matching the geometry of the two images with respect to their ground coordinates, actual coordinate systems, and creating the DTM and DEM. Now, the distortions are two types which are present on the satellite image or the digital images, systematic distortion and the random distortion. Now, these systematic distortions are predictable. We can apply the model, we can apply the correction very easily, because we know the behavior of these, either positive or negative. But random error, very difficult to find out, and its behavior is also unpredictable, because sometimes it could be negative while other times it could be positive. So, we can see that there are various kinds of errors which could be present in the satellite image. So, this is the due to the error in the height. If there is error in the height, then V by H error is there, then you may have a different coverage in the subsequent images. Then you can see the skew error could be present in the where the data is skewed because of the moving part of the scanner, as well as movement of the satellite in the orbit and the rotation of the earth. Then we have a distortion due to the curvature of the earth. So, due to the curvature of the earth, you can get lot of distortion. Then we can get the skew of the scan lines, because when the earth surface is scanned, by the time the satellite has moved downward by a certain distance, so we get the skewed image in that case. Then we have the projection distortion error. If we are not selecting the right kind of a projection, it depends upon the size of the area in which we are working. Then there could be a scale error. So some images are taken very high altitude, some images are taken from a low altitude, and relief displacement error. So these are different ways of uh, showing diagrammatically how the errors, different errors which could be present in the images are affecting the geometry of the image and in a way distorting some of the objects, and ultimately the measurements may not be correct, or whatever quantitative data we are deriving from that may not be correct. Now systematic distortion we like to correct through the modeling because we know actually its behavior. Now one of the example is the rotation of the earth. So there is a rotation of the earth and there is a movement of the satellite in the orbit around the earth, and there is a scanning part in the mirror in the sensor. So there are three rotations there involved, and sometimes because of that also we get the error present in the data set, which is the systematic error. So let us try to actually remove those systematic error. But when we have the random distortions which are present, then you have to actually use some kind of a mathematical transformations for that, because we do not know its behavior, and so we have to use some kind of a transformation equation, and this transformation equation we are representing in terms of the x is equal to f1 xy and y is equal to f2 xy, where x and y are the pixel locations, right. So x and y are the pixel location which is to be transformed, and x and y are the corrected coordinates which are known to us, let us say the real world coordinates which are known to us, and f is a function which we are applying to the pixel. So this is one thing what we are doing with the help of the ground control point, and the second process which we are doing is the resampling process. So these two processes are applied simultaneously in order to remove the error, minimize the error. So when we are doing that image registration process, what we are doing, we are trying to establish a correspondence between the two images or more images which we are using. So if we are using two or more images, then we are trying to establish a correspondence, a relationship between them, so that one pixel of the image lies exactly over the second pixel of the image and the third pixel of the image at the same geographical locations. So in a very simple way, what we are doing here when we are removing that distortion in the image, we are doing the rotation of the image, we are doing the scaling of the image, and we are doing the skewing of the image. So these three part we are doing, and this is done mathematically. So by choosing a polynomial. So if we use the mathematical equation, then we can apply these corrections, and let us understand how we do that. So in the process of georeferencing, we have to use some ground control points. So ground control points should be from the known reference, from the known image, and we have the unknown image or image which is to be georeferenced. So we have the image coordinates from the image which is to be georeferenced, and we have the actual coordinate, ground coordinates from the known image. Now we have to identify the same points on both the images. One is my, let us say, the master image, another image is the which is to be corrected. We have to identify what are the common points which we can locate on that. They should be very peculiar point. Now once we select those points, identify the coordinates, note down the coordinates of the two sets of images, then we have to select a transformations. So a mathematical transformation is selected so that we can apply that transformation, and by doing that we are establishing a relationship between the two images. To unknown image coordinate system, we are transferring it to the known image coordinate system. So that is the relationship which we are establishing, so that if we give input from the unknown image as a coordinates, we get the corrected output coordinate system. Now we are then computing the RMSE, root mean square error. We have the known coordinates of the points and we have the computed coordinates of the same points, and using these two values we are computing root mean square error, and we have to see that how to minimize that root mean square error. So in one go maybe we may not get the desired root mean square error, and so we have to maybe the iterate this procedure, but this is the complete procedure which one has to use for georeferencing. So when the control points are required, this is the primary requirement. So collection of the control points could be either from the reference map, the best source is the topographical maps, because they are available to us, and latitude and longitude lines are marked. So we can always find out peculiar features and determine the coordinates of those points from the topographical maps. But it could be other sources as well. We can take help of like the images, Iconos images or the other images which are present on the Google Earth, in order to identify which could be the best control points, peculiar control points, prominent control points. Then sometimes we have to carry out a physical survey on the ground in order to establish the points and then identifying those points on the images. So it could be any survey, GPS based survey, total station based survey or the LiDAR based survey. So where we know exactly the coordinates of the points from the primary survey, or sometimes we use the existing aerial photographs in order to, if we know the GCPs in the aerial photograph, the same GCPs could be used, ground control points could be used. So this is the procedure to collect the control points. So once you have a reference image where you are collecting the control point and you know the coordinates of those points, what we are assuming is that these coordinates are error free. There is no error present in those coordinates, and then we have the image which is to be registered. So in the image also we identify the same points and try to actually note down the image coordinates. So we have one set which is the real set, real world coordinates, another set is the image coordinate of the same point. Now there are two sets of coordinates, we have to establish the relationship between the two. So this is a slightly work which has to be done very carefully, because these when we are selecting the GCPs, very important thing is that they should be prominent point which you can locate, because otherwise if there is some error in locating on the image which is to be registered, then you may get a large RMSE error. So this should be within a pixel only when we are trying to locate. So it could be road intersection, could be sharp river bends, or could be very distinct natural features, and you have to blow it up on the screen so that you can see up to the pixel level and try to identify the point there, because if you are away 2-3 pixels, then you are bound to get large root mean square error. They should be well spread across the image. This is also there, should not be confined to the one area, otherwise that particular area will be perfectly geometrically registered afterwards, and the other area will have the lot of distortion. So that the entire image is geometrically corrected to the best possible way, we are trying to select the points which are well distributed in the area. They should also cover the maximum and the minimum elevation. So this also we have to ensure either from the topographical maps or of our GPS survey which we have done, that we are trying to select the control points which cover the minimum elevation and the maximum elevation because of the relief displacement which is present in the image. Then the number, how many points we should select. So this also depends upon the degree of polynomial. We will discuss this point while explaining you the polynomial. But how many points should be selected, this is also very, very important, and normally what we do is we select more number of points than what is desired. Now this is the ground control point which has been selected on one reference image, which we consider as the corrected image. The other one is the green marking of control points, same control points we are selecting on the other image which is to be georeferenced together. So once we are doing that georeferencing, you know what happens is that suppose I have 2005 image which is the corrected image, and that is why you can see the format also of this is aligned with respect to the geometry of the earth. Then I have another image of year 2010. Now I have to use these two images, and I have to see what are the changes which have taken place over a period of 5 years in the area as far as the river is concerned or as far as the urban area is concerned. So this 2010 image I have to register on the 2005 image. This is called image to image registration, image to image georeferencing. So when we are doing that using the procedure which I have explained you, you can actually now do the transformation part and resampling part in order to do that. So we are selecting a mathematical equation. Once we have selected the control points, now mathematical equation is to be selected, and then afterwards we have to do the resampling process, which you will learn in the next lecture. So these two processes will allow the image to fit together. So in the transformation process, you are establishing a relationship between the two, and in the resampling you are assigning the new values to that particular pixel location based on the DN values in the area. So here this diagram shows that the equation which is written here, x is equal to ax plus by plus c, and y dash is equal to dx plus ey plus f. This is the first order polynomial. So the first order polynomial has been selected, and here a, b, c, d, e, f, they are unknown. So our job is to find out these unknown. So you have to devise in order to derive 6 unknowns, you have to derive 6 equations. So you can derive 6 equations from the 3 points. So that means if I am using first order polynomial for georeferencing purpose, minimum 3 are required. But normally we take more than 3 points because some point may give me larger error. Then in the second iteration I have to discard that point. Another important thing which is to be remembered is when you are displaying the image. So this is the image. When you are displaying the image, the top left hand corner is your origin. But when we are talking of the coordinate system, then the bottom left hand corner is my origin 0 0. So the 0 0 or the origin is in a two different way when we are measuring the coordinate systems from both the images. So this you have to bear in the mind. Now after selecting the equations, this is the first order polynomial. After selecting the equation, you know how many unknowns are there in your equation. If you go for second order polynomial, you will have more number of unknowns. So in this case there are 6 unknowns, a, b, c, d, e, f. So as I told you that minimum 3 points would be required so that you can solve the unknowns, and once you solve the unknowns you have to keep the values of these coefficient in the equation, and you have to apply this equation to the entire image which is to be georeferenced. So in this equation on the left side, x dash and y dash are the known points from the reference image, and x and y are the coordinates of the pixel from the image which is to be georeferenced. Now first order polynomial, if we select, what happens now? It will require 3 GCPs. We are using first order polynomial if my area is very small or area is flat. We do not have much of the undulations in the area, because still 3 points when we are selecting, still we cannot say that they are the well distributed, because one corner is still left, and you may have a larger error in that region if the area has lot of undulation. So if the area is very small, because it is fast method, it is a very quick method, you are selecting less number of point. So first order polynomial will give you uh, sufficient accuracy results. But normally, what we do is we go for a second order polynomial, because so that you can select the points which are well distributed in the entire region, and this minimum of 6 points are required. So minimum 6 points, 4 corners and 2 in the center, so that you control the entire interpolation of the data. So normally that is what we do, 6 control points we select, and we are actually using it for the large area, and earth curvature is also taken into account in the second order polynomial. Then we are going for the third order polynomial, where minimum of 10 GCPs are required. So if the terrain is very rugged, very rough kind of a terrain is there, then we are going for the third order polynomial. So depending upon the accuracy which is desired, third order polynomial or the second order polynomial is definitely going to be much more accurate than the first order polynomial. So this is, then we are calculating the root mean square error. This is equation is showing the second order polynomial, where x is equal to b1 plus b2x plus b3y plus b4x square plus b5y square plus b6xy. Then we are calculating the root mean square error. We know the coordinates of the ground control, some ground control point, and we can compute and know the root mean square error, and we calculate this root mean square error should not be very large, should be plus minus within 1 pixel. So this example is showing you that the georeferenced data. So all the 3 images, this is thematic mapper images, all the 3 images now are georeferenced and georegistered, and we can use them together. So I was showing you this image 1995 and 1998 images is to be georeferenced, and you can see here now this 1998 image is also georeferenced, because you are getting now the same orientation of the image as the 1995 image. But if we have to compare this 1995 image with the other images also, if I have successive images to compare the area, then this is 1998. Now they are all perfectly registered, and we can see that exactly the details are matching over the each other, and we can visually also see the urban area is growing, that pink area is urban is growing, and the floodplain is shrinking at that particular point, because people are encroaching into the river system. Then the 2000 image, further the urban area has grown up, and 2005 image. So all that you can superimpose them together, you can create the animation, and you can find out what are the changes which have taken place over a period of time. This is 2010 image. So whenever we want to study the sequential images, their registration is very important, so that you can do that. Now if I am going for higher order polynomial, it is not necessary I will get the high accuracy. So it shows that here, that if I am going for the third order polynomial, image gets distortion. So it is not necessary I go for very high order polynomial, select very large number of control points, and still get the better accuracy. This curve shows on x axis. What I am showing you is basically the first order polynomial, the second order polynomial, third order polynomial, and the accuracy level. The best accuracy here is achieved by the first and second order polynomial, and not the third order polynomial. So it depends upon my areal extent, and depends upon that the total area. Now first order polynomial is very commonly used, as you will find that a lot of people have used this polynomial, and this particular polynomial is much faster, as it requires only 3 control points. So you select the 3 control points, apply it together, and if you want, if you feel that RMSE error is more, then discard that point which is giving more RMSE error, and select the new point. So this is slightly iterative kind of a procedure. The control points which are giving me larger error are to be neglected from the computation and selected afresh. When we are transforming the image with the help of the higher order polynomial or the lower order polynomial. The higher order polynomial will take much more time also, because image processing time taken will be more, also the selection of the control points will take time. So, map overlay analysis can be carried out once the images are georeferenced together. You can apply the geometric corrections to the images in order to carry out the change analysis, in order to carry out the measurements from the data. You can create vector data. That is what we are also doing in the GIS, for the GIS work. So, a lot of images are used to create vector data, let us say identifying the road network and giving input to the GIS system. So, there are lots of applications, advantages of correcting the data geometrically. So, this is all about the chapter.